The air over our major cities is turning to poison, and for days, every headline across the continent has been looking directly at the orange haze drifting down from the north. We are watching the dry northern forest burn, and we are told that is the story of the week. But while our eyes were fixed on the smoke, the exact same overheated atmosphere was quietly doing something on the other side of the map that is killing people faster right now. In the hills west of San Antonio, Texas, the sky did not fill with ash. It filled with water, and then it let go. In a single 72-hour stretch, roughly 3.8 billion cubic meters, that is 1 trillion American gallons, of water fell across a handful of counties. Rivers rose faster than people could wake up and run, and 4 separate major river systems flooded simultaneously. Most of the coverage treats these as 2 unrelated headlines competing for your attention. They are not 2 stories. They are one single story told in 2 opposite physical languages. The title sells the dramatic headline, but here is the precise correction. The flood in the south is far worse than the wildfire crisis in the north, not because fire is trivial, but because the water came faster, arrived in the dark, and killed directly in a way that smoke does not. The exact same atmospheric warming that is starving the northern boreal forest of moisture is the exact mechanism that loaded the sky over Texas and dropped a moving vertical wall of water on sleeping communities. To understand how catastrophic this is, you have to look at the numbers coming off the monitoring stations. On the Guadalupe River, a single gauge recorded a rise of over 7.6 meters, more than 25 feet, in just 60 minutes. That is not a river easing over its banks and gently filling a street. That is a vertical surge of water the height of a 2-story building, loaded with uprooted trees and debris, moving downstream at highway speeds. Upstream near Center Point, the river climbed nearly 10 meters in 4 hours. At Comfort, the Guadalupe reached 11.3 meters, climbing past the mark set during the deadly floods of 2025, and approaching an all-time record that has stood since 1869, back when Ulysses S. Grant was in his first year as American president. The mechanism behind this surge comes down to fundamental physics and local geology. When heavy rain falls on the Texas hill country, it lands on thin soil sitting over solid limestone. It cannot sink in. Instead, the steep slopes of the Balcones Escarpment act like a giant funnel, directing hundreds of millions of cubic meters of runoff straight into narrow river channels. Add to that a stalled weather system, a mesoscale convective vortex, that parked itself over the region, and you get a relentless moisture assembly line. Right now, the Canadian Hazards Information Service and Natural Resources Canada are monitoring our own seismic and atmospheric baselines, while south of the border, the National Weather Service issued a flash flood emergency, its highest possible alert category. Over 20,000 people were ordered to evacuate. State authorities deployed 2,300 responders, including Black Hawk helicopters, and more than 250 swiftwater rescues were carried out in the dark. The question this entire episode answers is simple. How can one single atmosphere create 2 opposite, unprecedented disasters at the exact same moment? And why is the wet half of that equation moving faster than our defenses can react? A single painted notch on a stone bridge pillar in the town of Comfort sits at 12.89 meters above the dry summer riverbed. For 157 years, engineers, hydrologists, and emergency planners treated that mark as the absolute physical upper bound of what this river system could achieve. It was notched into the rock during the legendary flood of August 1869, when Ulysses S. Grant was in his first term in office, long before modern dams, satellite telemetry, or radar networks existed. For more than a century and a half, every piece of flood defense, every highway culvert, and every emergency response protocol across this entire basin was calculated on the assumption that the 1869 watermark represented the maximum theoretical output of a worst-case storm. That assumption is now dead. When people hear about historic flooding, the loose framing usually suggests a random, freak act of nature that simply exceeded expectations. But the precise reality is far more compelling. We are watching an engineered hydrological baseline, refined over 150 years, completely disintegrate under a fundamentally altered atmospheric regime. The baseline was not a guess. It was a rigorous statistical model built on more than a century of physical river gauge data collected by agencies like the Geological Survey and maintained through modern automated hydrometric stations. To understand why this system is breaking, you have to examine the historical design parameters. In the late 19th and early 20th centuries, hydrologists mapped the regional river network, focusing on four primary conduits: the Guadalupe, the Pedernales, the Frio, and the Nueces. They calculated peak discharge rates based on the physical limits of the atmosphere at the time. The historic baseline assumed that while severe convective storms could park over the escarpment, the total precipitable water in a given column of air had a strict thermal ceiling. In the Great Flood of July 1932, the Guadalupe River at Comfort peaked at 11.1 meters, delivering a discharge rate that reshaped the valley. In August 1978, Tropical Storm Amelia dropped massive rainfall, pushing the Pedernales River to 10.1 meters near Johnson City. In every historical instance, the flooding was severe, but it remained within the statistical envelope of a 100-year or 500-year event. Crucially, these historical events were isolated. One river basin would experience a catastrophic surge, while neighboring catchments handled moderate runoff. The regional infrastructure, including flood retention dams, spillways, and raised bridge crossings, was explicitly engineered on the assumption that a multi-basin simultaneous peak across all four river systems was physically impossible under standard atmospheric moisture limits. The mechanism that maintained this historical baseline was thermal limitation. In simple terms, a cooler atmosphere can only hold a finite amount of water vapor. Standard atmospheric physics dictate that for every 1 degree Celsius increase in temperature, air can hold approximately 7% more moisture. During the 20th century, peak summer air masses over the continental interior held precipitable water values that rarely exceeded 35 to 40 millimeters. That moisture load set a hard ceiling on rainfall rates. A heavy cell could deliver 25 to 50 millimeters of rain per hour, but it would deplete its moisture supply rapidly, forcing the storm to dissipate or move on before completely saturating the deep bedrock storage. Furthermore, historical civil engineering accounted for the region's unique karst topography. The underlying limestone bedrock, cut by ancient fault lines along the escarpment, was known to convert surface rain into immediate runoff. But the historical baseline assumed the ground itself acted as a buffer during the initial hours of a storm. Soil moisture levels were historically variable, allowing the first 50 millimeters of rainfall to be absorbed into fissures, sinkholes, and subsurface aquifers before surface channeling began. That historical buffer no longer exists. Between 1900 and 2020, hydrometric records showed a stable pattern of return intervals. A flash flood reaching 6 meters above gauge zero occurred roughly once every 15 years. A 9-meter surge was a once-in-a-century event. The 1869 record of 12.89 meters stood as an untouchable monument to an extreme past. But over the last 2 decades, the baseline began to warp. The return intervals compressed. What used to be a 50-year flood level began appearing every 8 to 10 years, culminating in back-to-back generational surges that have brought the water right back to the top of the 1869 notch. A digital reading on a display at the Atmospheric Monitoring Station in Corpus Christi registered precipitable water levels exceeding 52 millimeters, more than 2.0 inches, at precisely 3:15 UTC. Across the continent, sensors operated by Environment and Climate Change Canada were simultaneously logging record-high upper atmosphere thermal values right up to the Canadian border. The popular framing of this catastrophe claims that a random, localized cloudburst simply overflowed a few riverbanks. But the physical reality is far more complex and dangerous. What actually failed was the atmospheric speed limit that normally prevents rainstorms from parking over a single piece of land. The mechanism behind this breaking point operates through a distinct sequence of thermodynamic steps. It begins over the Gulf of Mexico, where elevated sea surface temperatures drive intense evaporation. That moisture is pulled north by a low-level wind jet, feeding directly into a mesoscale convective vortex, a compact, rotating low-pressure weather system between 30 and 60 kilometers wide. Normally, a thunderstorm carries its own off switch. As rain falls, it cools the surrounding air, creating a dense wedge of cold air known as a cold pool. This cold pool acts like a plow, shoving the storm across the landscape so its water is spread out over hundreds of kilometers. In this event, that self-correcting engine broke down entirely. Because the incoming air was so utterly saturated with moisture, falling rain could not evaporate into dry air on its way down. Without evaporation, the air could not cool, and the cold pool never formed. Stripped of its internal push and with weak steering winds aloft, the storm stopped moving. Instead of traveling across the continent, it set up over the Balcones escarpment, locked in place by a stalled weather boundary. What followed is a phenomenon meteorologists call training, where individual convective cells form, pass over a target area, dump their water, and are immediately replaced by new cells forming right behind them along the exact same track, like cars on a train. When this moisture assembly line operates over thin soil and solid limestone, the Earth reaches total saturation within minutes. Every single drop that falls after that point becomes instant surface runoff. This is where the old hydrologic models and historical data completely fail. Civil engineering designs, whether for culverts in southern Ontario, dam spillways managed by BC Hydro, or river channels in Texas, were built on historical rainfall intensity duration frequency curves. Those curves assumed a strict maximum rate of rainfall per hour. But when precipitable water values exceed 50 millimeters in a warm atmosphere, rainfall rates can reach 100 millimeters, nearly 4 inches per hour. Instruments across the monitoring network, including automated hydrometric stations monitored by federal agencies, track this mechanical failure in real time. Microwave radiometers and Doppler radar units recorded storm cells regenerating over the exact same coordinates for hours on end. The consensus among atmospheric scientists is unequivocal. The historical baseline model is no longer valid because the atmospheric moisture capacity has fundamentally shifted. The thermodynamic ceiling was breached, and the physical engine designed to keep storms moving simply turned off. A red electronic map display in the Regional Emergency Operations Center showed 87 separate highway closures across a single jurisdiction simultaneously at 4:30 local time. Drivers attempting to navigate what appeared to be standing puddle water on primary transit routes were actually crossing places where the roadbed had been entirely hollowed out from beneath the asphalt. The standard headline coverage frames this escalation as a routine seasonal inconvenience, suggesting that roads will reopen as soon as the water recedes. But the far more consequential reality is that a moving volume of 3.8 billion cubic meters of water does not merely cover infrastructure, it structurally deforms it, severing supply chains and compromising critical utilities in ways that take months or years to repair. To understand the physical scale of 3.8 billion cubic meters, picture a volume of water equal to the entire annual municipal consumption of a city like Toronto or Montreal, dropped onto a single rural region in under 72 hours. When that mass hits the ground, 1 cubic meter of water weighs exactly 1 metric ton. Moving at high velocity down a narrow river valley, that volume exerts thousands of kilopascals of hydrostatic pressure against anything in its path. In Kerrville, the Guadalupe River pushed large commercial barges upstream off their moorings, slamming them into main arterial bridges with enough kinetic force to force municipal engineers to close major structural crossings indefinitely. The real-world impact cascades immediately into daily life. At the water treatment infrastructure in Kerrville, heavy sediment loads and direct flood inundation compromised filtration systems, forcing municipal authorities to shut down clean water distribution. Sewage lift stations were overwhelmed, sending untreated effluent back through urban networks. The provincial and regional alert systems, including Public Safety Canada's alert-ready equivalents across transboundary networks, pushed top-tier emergency notifications directly to mobile phones in the middle of the night. At least 125 distinct road segments were submerged or washed out, severing primary supply corridors and turning populated rural districts into isolated islands. This infrastructure collapse is not isolated to Texas. It mirrors the physical vulnerability demonstrated during the November 2021 atmospheric rivers in British Columbia, which severed every rail link and highway connecting the Port of Vancouver to the rest of Canada. When a loaded atmosphere dumps extreme rainfall rates over steep terrain, the critical links of modern life, asphalt highways, rail passes, drinking water intakes, and municipal power grids, are severed simultaneously. For ordinary residents, the escalation manifests in minutes. Families in Kerrville were forced into attics at 2 a.m. as floodwaters rose to waist height inside their living quarters within minutes of the initial breach. Emergency responders carried out over 250 swiftwater rescues using Black Hawk helicopters and specialized floodcraft, navigating dark waters littered with propane tanks, heavy timber, and downed electrical lines. The physical energy contained in moving floodwater means that just 30 centimeters of swift current can sweep away a standard passenger vehicle, while 60 centimeters will float an SUV. This physical reality explains why vehicle-related drownings accounted for the primary casualties during this event. The total economic cost across the 59 declared disaster areas is estimated to exceed billions of Canadian dollars, transforming what was once framed as a localized storm into a macroeconomic shock across regional supply networks. 4 separate river basin monitoring stations spanning a distance of more than 200 kilometers all registered peak crest alerts within the exact same 12-hour window. The Pedernales, the Guadalupe, the Frio, and the Nueces, 4 independent drainage networks, all overflowed their historic channels simultaneously. The standard dramatic summary of this crisis claims that we are looking at a permanent, unending state of extreme flooding that will immediately swallow every river valley on the continent. But the honest scientific boundary is far more nuanced. What is established beyond debate is that the atmospheric moisture floor has permanently shifted upward, while what remains unresolved is whether civil engineering and emergency management can adapt quickly enough to prevent these back-to-back disasters from becoming the default state of every summer. What is unequivocally established by physical data is the thermodynamic link. A warmer atmosphere holds roughly 7% more water vapor per degree Celsius, and the Gulf of Mexico delivered precipitable water values exceeding 52 millimeters directly into a stalled mesoscale convective vortex. The land, constrained by thin soil over limestone, converted that volume into immediate surface velocity. What remains genuinely unresolved among atmospheric scientists and hydrologists at Natural Resources Canada and international monitoring bodies is the exact future behavior of steering currents. We do not yet know if jet stream stalling will become a permanent feature of every summer pattern, or if this stalled vortex represents a rare confluence of atmospheric factors. To know which way this system goes over the coming weeks and months, there are 3 specific, checkable developments you can watch on public data feeds. First, check the Oceanic Niño Index and sea surface temperature anomalies published for the Gulf of Mexico and the equatorial Pacific. If sea surface temperatures remain more than 1.5 degrees Celsius above baseline, the atmospheric load will remain primed for repeat training events. Second, watch the official hydrometric gauge readings at Comfort and Kerrville. If the Guadalupe River experiences a secondary crest above 8 meters before the ground fully drains, downstream flood levees will face structural failure. Third, monitor whether Environment and Climate Change Canada, or the U.S. National Weather Service, issue formal advisories expanding flash flood emergency protocols into upper-tier convective models across central transit corridors. Until one of those 3 checkable markers occurs, the situation is plainly this. We are living under an atmosphere whose physical capacity for carrying water has outpaced the historical design limits of the infrastructure beneath it. The fire in the north and the wall of water in the south are not 2 separate stories competing for our attention. They are simply the intake and the exhaust of the exact same heat engine. Tell me in the comments where you are watching from tonight. If you value this deep analytical breakdown, hit like and subscribe to stay